Welcome to RF 101 Labs. This is Ruby Singh. Today we're going to be talking about RF applications and give you many exciting reasons to want to become an RF engineer. All right, let's get started. Okay, let's start off by talking about everyday RF examples. Obviously, one of the very first example is a device that we use every day, and that is a smartphone. Another example would be cellular base station. These would be from your cell phone carriers like AT&T, Verizon, Sprint, or T-Mobile, and that's if you live here in the US. If you live in other places such as UK, it might be carriers like O2 or BT. Another example would be Wi-Fi. Your laptops, smartphones, and all your smart home connected devices such as thermostats, alarm systems, security cameras, garage door openers, and even smart lights. These are all connected to your Wi-Fi router. Another great example is GPS. As you might know, GPS stands for Global Positioning System. Through the innovation of GPS satellites that are orbiting around Earth right now, your smartphone's GPS receiver can tell you where you are on the map. It does this by triangulating the signals from multiple satellites. So we're going to be talking more about this in another video, so stay tuned if you're curious. Another example is televisions and radios. Last but not least, one of the things you might not even have heard of is RFID tags. RFID stands for radio frequency identification. You'll find RFID tags inside tap and go credit cards. You'll also find RFID tags in products at your local markets. So the wireless industry is an ever-growing market, with more and more companies trying to make their products wireless, and due to the exponential growth in IoT devices being Internet of Things, there just aren't enough radio frequency engineers being trained to keep up with the demand. So I think there is a huge advantage to learning RF engineering and wireless communications in general. One of the things I want to mention is that I haven't even listed the entire RF industry. These were just some of the few examples that we might come across every day. What you might not realize is that RF in medical field is a pretty big thing. One of the first examples I would like to give is a hearing aid. A person wearing a hearing aid probably doesn't want a bunch of wires dangling out of the ears. So a wireless hearing aid is a great innovation that improves people's lives. And one of the best medical field examples I like to give is an MRI machine. MRI stands for magnetic resonance imaging. Many of you might not realize that MRI fundamentally works due to a radio frequency called Larmor frequency. It's named after Sir Joseph Larmor, who was a physicist and a mathematician. There is no doubt that when MRIs were invented, it significantly changed the medical field forever. Another example where you might find radio frequency use cases, cardiac rhythm monitor. All right, moving along to the next example, wireless blood glucose monitor has become quite a commonplace nowadays. Your doctor is able to monitor your results remotely to see how your treatment is coming along. And lastly, RF is being used to treat liver cancer. It's a procedure called RF ablation, in which a doctor will insert a needle probe into a patient's liver and pass RF currents through the probe. This generates localized heat in the tumor and destroys cancer cells. All right, now let's shift gears and talk about one of my favorite topics, and that is radars. Radar stands for radio detection and ranging. Radar is used across many different industries, as you'll see in the following examples. One of the first examples where radars are used is in the automotive industry. Usually these radars operate at very high frequencies known as mmWave band, and that's done to take advantage of the small wavelengths for resolving small details in an object. Two main frequency bands that FCC has allocated for this application are around 24 GHz and around 77 GHz. There are some distinct advantages to using radars when compared to other detection methods such as LiDAR or ultrasonic. LiDAR uses lasers to bounce light off of objects. While LiDAR is really good for creating sharp and accurate images of a surrounding, it does have some downsides. LiDARs are currently super expensive, and they get affected by environmental factors such as rain, fog, and even temperature. On the other hand, radars can travel very long distances and can penetrate through fog and rain and aren't affected by temperatures either. Radars have been very reliable systems for several decades now. However, that being said, we should not look at LiDAR and radar as competing technologies. but rather complementary technologies. If you take best of what each technology has to offer, you can design the best detection and ranging system. In the future, I'll be making videos to explain how each technology works in depth and why you might want to choose one technology versus the other for your application. Another very common application for radar is in the aerospace and defense industry. Commercial airplanes and military fighter jets use radars to scan for threats far away. It's very important for fighter jets to know when an enemy airplane or a missile is 50 or 100 kilometers away. Radar is your best bet for detecting that object and taking corrective action in time. And lastly, radars are also used to scan weather conditions. Your local news channels often use Doppler weather radars to produce local weather forecast. Alright, moving along. Another new exciting field where RF is highly being used is quantum computing. Quantum computing relies on the fact that fundamental particles such as photons, nucleus of an atom, or electrons have a property called quantum spin, which can either be spin up or spin down, and that can be translated to being 1 or 0 in binary. However, since this is a quantum system, it exists in a superposition of 1 and 0, and it's not until a measurement is made that will cause the quantum spin to collapse into a deterministic state of either a spin up or a spin down. Physicists and engineers are using this superposition to exploit powerful computational properties. Quantum computing is still in its infancy, so you might ask, how does this relate to RF? Well, microwave pulses are used to change the quantum state of the particles at their resonant frequency. In fact, what you're seeing in this image are a lot of RF circuits, such as coaxial cables, couplers, circulators, that are carrying the RF signals. As quantum computing field matures, you can bet that the demand for the RF engineers will continue to grow exponentially. Let's discuss another use case of RF. Have you been to any airport lately and you get body scanned with a machine where the agents will ask you to put your hands above your head? Well, there's a high chance that the scanner is using millimeter waves to scan you. The benefit of scanning using millimeter waves compared to X-rays is that X-rays are considered to be ionizing radiation, which means the photons in X-rays have enough energy to knock out electrons from atoms in your body. However, millimeter wave photons are much lower energy and are considered to be non-ionizing. Let's move on to one of the most inspiring topics, cosmic microwave background radiation, or CMBR. In 1964, two radio astronomers, Robert Wilson and Arno Penzias, pointed their radio telescopes in the sky. What they discovered was that there was a source of hiss or noise that they couldn't explain. No matter where they pointed their telescopes in the sky, they got the same exact result. They initially thought that this could be interference from the radio itself or was coming from the nearby city of New York. Once they ruled those out, they thought maybe it was caused by the pigeon poo in the horn antenna. Once they cleaned that up, the hiss was still there. When they couldn't explain it, they called up an astrophysicist, Robert H. Dickey, at Princeton University, and it turned out what they had discovered was the cosmic microwave background radiation, or CMBR. CMBR is the remnant of early stage of the universe. This discovery provided the much needed evidence to back the Big Bang Theory. Due to their discovery, the astronomers won Nobel Prize in Physics in 1978. I hope to do another video on this topic in the future as it is really interesting. And to wrap up this video, I want to leave you with an interesting fact. How far do you think we can communicate with radio waves? Well, the answer is really, really far. One example I can give is that NASA is still in contact with Voyager 1 probe that launched in 1977. Voyager 1 entered interstellar space in 2012, becoming the first human-made object to do so. Currently, it is astonishingly 23.3 billion kilometers away. To put things in perspective, it takes radio waves traveling at the speed of light 21.5 hours to reach Earth from Voyager 1. This means in order for NASA to send a command and wait for a confirmation, it takes close to 2 days. To put things in another perspective, that's roughly 156 times the distance from Earth to the Sun. Wow. If that doesn't blow your mind, I don't know what will. Well, that's it for this video. I hope with all these examples you're now interested in learning more about RF and wireless communications in general. And I hope I have portrayed that RF is everywhere.